to another RDWorks Learning Lab. I think today's session is going to be quite short. I think I may well have now finally cracked the aliasing problem. Now if we catch those in the light, you see I've managed to do quite a lot of testing here, but that target there is 10 kilohertz. And then I started off again at 10.001, 10.002. In other words, I added 1 hertz to each one of these and checked what was happening. We're not talking about 10 or 100 hertz, we're talking about increments of just literally 1 cycle per second in 10 kilohertz. And the one that came out best was this one here, which is 9.999. So that's 1 hertz off of the target 10,000, and that's almost aliasing free. I will show you that under the microscope shortly, compared to that one which we know as rubbish, which is quite amazing. Literally 1 cycle per second and it changes the aliasing. Now I thought my previous image was pretty good. I can already see some amazing differences on here. So it's gone from pretty good to almost perfect. We'll compare the results when this is finished. So basically I've used my checker pattern to do 2 things. First of all, to try and get rid of the aliasing, and secondly, I've been very accurate in the way in which I've set my scanning offset up, because my scanning offset is now set to better than 0.1 of a millimetre. In fact, it's set to 0.05 of a millimetre. I'm running this at the settings I use for my checker pattern, which is 1000 millimetres a second as opposed to 1200 millimetres a second, which I did for the first one. I have no doubt that I could run this at 1200 millimetres a second. I could use my checker pattern to set up the scanning offset perfectly, and I could also use that same checker pattern to check for the least amount of aliasing, whatever frequency that happens to be. It could be just 1 or 2, as in this case, cycles per second, staggering the difference. As I said before, your eye is being fooled by these millions of little dots. The spacing that they have between each other and their relativity to the dark background in this case, because we're producing white dots on a dark background, not black dots on a white background. So this is being done the other way around. And so this background here is very sensitive to the aliasing patterns as we saw before. 21 minutes 34. I've increased the power from 25 to 50 because this is a different material. I've got titanium dioxide on the surface here, on the surface of a white tile. And so we're going to attempt almost the Norton tile method of creating a dark image at 1000 millimeters a second. Now you probably can't see that at the moment, but where this was going backwards and forwards very quickly at the beginning, just here, there is a very fine end to a whisker. You can just see the whisker beginning to thicken up now. As I demonstrated to you in the last video, this image has not been tampered with in any way at all. It's the original photo with the colour removed, changed to a grayscale image and then dithered. So all we've got on this image is very small, 0.1 or less, black and white dots. Well, I'll change that slightly because I'm not producing any white dots, I'm only producing black dots. What's left in between is white. Now I want you to look at the clarity of those whiskers. They wouldn't be that thin and that clear if I had not got my scanning offset correctly set. So precision scanning offset is essential. This is not completely the Norton tile method because I've not sprayed this with white paint. This has been sprayed with pure titanium dioxide. It's quite difficult to get it on with an airbrush to a nice uniform thickness, and if you don't get it onto a uniform thickness, the picture will come out blotchy. Fingers crossed, we'll see how this goes. Well, while that's busy working away, let's go and take a look at the comparison between my first attempt and my second attempt at the Foxy picture on blue acrylic. Now, although this first attempt here was pretty good, but look, you can see the banding in it that I mentioned. Look at this second attempt. Look how crystal clear the eyes are. Look at the nose, the clarity and definition of the nose. And yes, we can see black nostrils on a black nose with a mere smear of highlight on there. But look how good it is on this one. Look how clear the eyes are on this one in comparison to that one. There's a certain amount of muddiness to this and fuzziness to this, which, without sitting it beside this one, you wouldn't even consider. This one is going to come out staggeringly good. I think that's basically case proven. I now understand how to do photo replication on this RF machine. And I can do it on acrylic, I will be able to do it on card, on wood, and we've also been able to do it with the almost Norton White Tile method at 1000mm a second. Took 18 minutes 34 to do that. Now, at the beginning of this video I mentioned it was going to be a short video. Well, I'm not really a believer in fate, but circumstances have conspired to make this video a little bit longer, because several different things have intersected with this project, which really have solved some problems that I've been looking for answers for several years now. Let me start the story off at the beginning. I was involved with some guys in the States who were very keen about digital graphics and dithered images. And one of the problems they regularly encountered was this banding on their images. They diligently searched for the problem themselves, and I was looking into the problem as well, but they came up with an answer which basically said, yeah, it's all to do with our CW 5000s or 5200s, our refrigerated water systems that we use for cooling the tubes. It made no sense to me that the banding that they were identifying was to do with the cooling turning on and off. The solution we talked about and they adopted was basically buffering the temperature change. They put in a reservoir rather than a CW 5000, and they put a normal submersible pump to pump the water through their tube. And then they used the CW 5000 feeding into a copper coil immersed in the reservoir. So the reservoir was actually acting as a temperature buffer to make the temperature changes a lot smoother. And that solved their problems. Now, I never did really understand why that fixed the problem, but it fixed the problem. We roll on 4 or 5 years now, and I appear to have some banding on my RF machine images. Now, I'm going to do something I don't normally do here, which is to mention people's names, because I've got 2 contributors that I must thank for solving this age-old problem. Not directly, but indirectly. A regular contributor to my beam conditioning work on the RF machine has been a guy called Danny Miller. Now, my goal was to try and make this 30-watt RF machine into a cutting monster by making the beam extremely small. Danny has been extremely enthusiastic about this work and has encouraged me to keep going and keep going and keep going, even though I was actually failing in my primary goal. Now, I haven't gone the direction entirely that Danny expected me to go, but at the end of the day, I've finished up with a super duper high intensity, very narrow beam that I've been able to control. Even though lenses don't really want me to, I've been able to control it into a very, very high intensity, small spot to do what you've seen me doing in these videos. Now, you won't be able to do what I've done with your RF machine if you have an RF machine, because you don't know what I've done to my beam. So indirectly, I've got to thank Danny for this, but there's another vital piece of information that I've got to thank Danny for. It's a piece of information that I completely disagree with, maybe. He's informed me that, yeah, my banding is due to temperature variation. He's found that a 1 degree C rise in temperature in his water cooling system produces a 1% power change. I've gone silent because many years ago I did some test work myself on glass tubes, and I ran the tubes from 12 degrees C all the way up to 45 degrees C. I only got a 5% power reduction after that huge temperature range. So look, we've got two pieces of conflicting information here. We can't both be right, or can we? We're going to cover that issue later on. So Danny's suggestion as to why my two dark bands appeared on the first picture cannot be true, because the RF machine is not a water-cooled machine, it's an air-cooled machine, and there is no power variation that can be occurring. What I need to do is to go back to my RF machine and the fact that I know absolutely that aliasing was the root cause of my problem. In fact, you've seen that it's the root cause of my problem because you've seen the significant difference between the first and the second attempt on acrylic. Now, I came across this piece of software while I was working with the fibre laser machine, and I wanted to use a demonstration about constructive and destructive interference of signals. This is an amazing piece of demonstration software that I've discovered on this site here called the Physics Classroom. I know that these are not pixels, and I know that these are not burning pulses from the laser, but these are signals that are simulating this condition. So these two waves are actually additive, and they produce a signal here which is twice as big as these two signals. This is not about wave addition and subtraction. Here we've got a simulation of pixels. So every one of these blue waves is a pixel, and every one of these red waves is a pulse generated by the laser to print one of these pixels. And as you can see at the moment, these are perfectly lined up, and we've got perfect printing of pixels. They're all exactly the same burn strength. If you only get a very, very small error between this signal and this signal, you get very, very slow and obvious changes to this signal. Now, I attempted to make my PWM signal perfectly match the pitch of the pixels, but something didn't go quite right. There was a very slight difference between the pixel and the pulses trying to make those pixels. Okay, so I've very slightly now just changed the frequency between these two signals. This one here, the pulse, is very slightly less than this one. And look what's happening to the signal. It's getting less and less and less and less. And I'm getting to the point now where all of a sudden I will have no signal. And then the signals will start getting bigger and bigger and bigger. With a very, very small error between these two signals, we get a very slow change. If I increase the error between the two signals, look what happens. It gets bigger and smaller quicker. And the bigger the error, the faster the changes occur. To the point where if I put a certain significant error in, like that, the error is so rapid that you might not even notice the problem, because the error is built in between lots and lots of pixels, and you wouldn't notice that some of those pixels were slightly smaller than the others. There would be an overall pattern change, maybe in the lightness or the darkness of the picture, but you wouldn't notice that pattern unless you were doing some very simple plain engraving where there's no supposed change to the background. You would then see that pattern in the background, as I demonstrated to you on some of my previous videos. So I found that I only had to change my pulse rate by 1 Hertz in 10,000 to get them to match and produce a nice error-free burning pattern. I will just remind you of the peculiarity of the RF machine. When the aliasing reaches a point where, as you saw, we get no output power, the problem with an RF tube is the power is always 100%. The thing that's changing is in fact the exposure time of that power, and as that exposure time increases, So what happens is the beam size, the dot, is increasing in diameter. So we're not getting a change of power directly, we're getting a change of exposure time, which changes the dot size. So last time when I did my more successful picture, the second picture that I created, effectively what I've done is this. I changed the frequency to 9.7 kilohertz instead of 10. And so I've got this very rapidly repeating but small pattern, which you don't really notice. But you've seen in today's image, when I get them to match perfectly, how all of a sudden it becomes super crisp, lighter, and we get more definition in the picture because we're getting perfect information in the picture, not distorted information in the picture. Right, so I think we can put our RF imaging to bed and say that any errors that I had in that were purely due to aliasing, but there can be no power variation in an RF signal. If the laser on signal is mismatching with the pixel signal, there is going to be a variable coincidence of exposure time that's going to produce this different dot size. So that's not a problem with an RF machine. It's something else, which is purely down to aliasing. Now that's not the case with a glass tube. A guy called Matthew Ullman, who I've been emailing for about the last 6 months. Now he produces some absolutely amazing images on slate. They're actually very, very good, and I'll show you one of his images shortly, and you'll understand what I mean. They don't require the subtle detail that you would get trying to produce a photo replication. And as such, he takes his images and he passes them through IMAGR to prepare them for lasering. But he has been suffering with banding on his images. And that's what we've been trying to resolve for the past 6 months. Now it's been a bit of an uphill struggle because we've tested all sorts of things about his machine. Basically we've dismissed the machine as being anything to do with the root cause of the problem. Before I came across the issue with RF, we started to look at this possible problems of aliasing, where the pixels were not matching the pulses for some reason or other. But he was using 300 pixels per inch for his images. And he was then passing them through IMAGR to process them. And when they came back as bitmaps, he didn't know this, but he sent me some images to look at, and I found that those images did not come back to him at 300 pixels per inch. Now here's one of his negative images that he puts onto slate, so that's why it's a negative image. As far as I can understand, he sent this image away as a 300 ppi image. By the time it's come back from IMAGR as 318.125 pixels per inch. So in Lightburn, he's going to set this to pass through. When you select pass through, you get no information here about the DPI. All that's going to happen is Lightburn is going to process this with 318 dots per inch. 25.4, divide that by 300 equals 0.08466. 0.0846. 0.0846. Okay, so there's my pixel size for 300 pixels per inch. I don't know that this is a 318.125 pixel per inch image. I sent it away as 300, it's come back as 300, and I've chosen 300. What I'm really now doing is I'm creating an aliasing pattern. Lightburn is going to turn the tube on and off for every single pixel that it sees. So there's going to be no problem in the x-axis, but the problem is going to be in the y-axis because he's stepping at a rate which doesn't match the pixel size. So you're naturally going to generate bands in the y-axis because of this difference in the pixel size and the y-axis step. Haha! So that's the reason why Matthew is getting banding. No, it isn't. Because the error is so large that you might get the odd line here and there. You don't get bands. Remember, you need very, very small errors to produce this banding effect or large visual errors. So it turns out that that error is not causing him the problem. Even though the potential is there to produce an aliasing problem. So as I said, it's an amazing coincidence how things have actually coincided and crossed over. Let's put all those coincidences together now, because Matthew, in the past few days, has done some great work, and it's repetitive work of what happened 6 years ago with the guys in the States. I know this guy's got a China blue machine. The one thing I was not aware of was that he's running this machine with a CW5000 or a CW5200, a refrigerated chiller system. He's recently sent me some definitive work which shows the way in which the chiller, switching on and off, is producing different density bands. The power is changing as the tube switches on and off. It's pretty obvious, isn't it? Remember what I said earlier? I've done tests on my tube between 12 and 45 degrees C, and I'm only seeing a 5% change. Danny tells me there's a 1% change for every degree C. As I said, this is the amazing coincidence of all this information coming together at one time. It's made me sit down and think long and hard, how can we both be right? It comes back to understanding where power variation actually is generated. Now I'm afraid I'm going to go off on one of my little scientific whizzy doodles. Now, here's a basic laser tube during manufacture. And I'm going to stop for a minute, and I'm just going to show you what happens during the manufacture of a laser tube. You can go and watch the whole of this video on YouTube. It's by EFR, a very good laser tube in manufacturing company, and it's called Laser Tube Manufacturing Process Video. I'm just going to show you one part of the manufacturing process, which is a vital part. They're very, very carefully grinding the end face of the laser tube at the same time. Two faces at the same time, because those are the two faces that they put mirrors onto. I'm not going to bother to draw the internals of what's happening in here with the mauve beam and all the rest of it. Those mirrors are vitally important. Any photon, and we get these little things in here, photons, which happen to be travelling in this direction, will hit this mirror and have got to pass back perfectly down the centre of the tube and reflect off this mirror, and then bounce back off that mirror and perfectly hit the surface of that mirror, to perfectly bounce back off there and then hit here in exactly the same spot and bounce back. And that bouncing is happening probably 1 billion times a second, amplifying themselves and creating ultimately the output that comes out of here, which is our watts. This is a 100% reflecting mirror, and this is, I don't know what percentage it is, but it's probably maybe say 90%. 90% of the photons that hit this mirror reflect back and get amplified as they bounce backwards and forwards, but 10% of those are leaking out of here to give us the power that we want. Now the important thing is, and I stress it again, is the perfection of mounting and flatness of these mirrors. If these mirrors are not flat, or they're not perfectly mounted parallel to each other, then what's going to happen? This photon here coming back may decide it's going to hit here instead, and it's going to bounce off there perfectly. But if this one is not flat, then the next time it's going to hit here, and then it comes back to here, and it's going to bounce off here. So eventually, after a few reflections, this photon that hits here is not going to hit the centre of the mirror. It's going to gradually move off. And if it gradually moves off, it means we're basically going to lose power. If you look carefully at your mauve beam in there, you'll see that your mauve beam, when you look at it from the side, it's difficult to see it. But turn the power down and you can clearly see that the beam, the mauve beam, has got a fairly sharp centre, and then it disappears away to almost nothing at the edge. It's a very fuzzy beam with a sharp centre, and as you increase the power, what happens is the centre becomes more powerful, but you'll still have very low fuzzy power right at the outside of the beam. So that beam is effectively what we normally see as this Gaussian distribution across the beam. So the pink beam itself is a Gaussian intensity distribution and is responsible for creating the intensity pattern in our invisible laser beam. So if we get any variation in the power down the center of the beam, because it's moving off to the side, we're going to lose intensity and we're going to lose damage capability. That's the essential part that I want to make you understand, the absolute need to keep those mirrors both flat and parallel to each other. One of the major things that happens is this process is very, very sensitive, as you can see. And if something does not quite work out right, the only time they're going to know something hasn't worked out right is when they put these to final test. They'll put a special test current through it and they expect a certain peak wattage out of this tube. So the tube fails to deliver its maximum power at test. What does that mean? Well, it means it's a B-grade tube, as I call it. It can't be warranted by the manufacturer. And basically, it gets sold for half of, not very much, to a grey market, which could be anybody selling tubes on eBay, but mainly it will be the machine builders themselves who will very happily take these tubes that work, but not to full spec. There's a pretty fair chance that anybody buying a machine will have a B-grade tube in it. One of the classical ways that you can detect a B-grade tube very, very quickly, from 0 all the way up to full power, will have a solid burn like that. If you find that you've got a burn which looks like this at low power, almost certainly you've got a B-grade tube. It's a classic symptom of a great B-grade tube. You've got no power right in the center of the beam. I've shown you what a sharp Gaussian distribution mode burn looks like. You run your beam into a piece of perspex for 10 seconds and that's the shape you expect to get. If you run your beam into a piece of perspex for 10 seconds and you see something that looks like this, B-A. That's all I can say. It's as simple as that. This is good at cutting. This will be okay for engraving, but pretty inefficient at cutting. But that's not what we're about today. What we're trying to find out is why temperature is affecting our power output. You can create a B-grade tube by distorting these mirrors. You can't change the parallelism. You've got an A-grade tube to start with, which is parallel. You can't make them any less parallel, but what you can do is cause the mirrors to somehow distort. Now, these mirrors get hot, and the way that the laser manufacturers deal with that problem is they encase the mirrors and they put water through them that then eventually goes back into your tube and runs around the outside of your tube to cool the main ionization tube. And then it comes out of here and it passes through another cooling chamber here and here. That's an interesting point, isn't it? We've got a conflicting requirement here. We need the mirror to be cool, but we can't have this mirror completely covered with water. We need an open space through the middle of it to get our watts out of. This mirror here is being 100% cooled across the whole of its flat surface, but this mirror here, it's only receiving cooling round a little annulus round the outside. So we've got a very flat glass mirror which has got cooling in an annular ring round the outside. Do we think that mirror is going to stay flat if you subject this to an instant shock load of cold water? Well, the answer is no. So consequently, we're going to get a distorted mirror like this, and we're going to have a lot more of these photons that don't actually make it on their back and forward return journey. So we're not going to get the correct amount of power out of this tube while this mirror is distorted. This explains why we've got this conflicting information between Danny and myself. On the one hand, I'm saying I can take this tube from 12 degrees C up to 45 degrees C, and it equals 5% power loss. Whereas Danny is saying 1 degree C equals 1% power loss. My facts and figures don't agree with Danny's, but there's a good reason why. My test was carried out over an hour and a half. My mirrors never had a chance to receive a shock cooling load. They were very, very gently changing shape, which would account for my 5% loss after an hour and a half. Whereas over a few seconds almost, a 1 degree shock power load is going to cause distortion to this glass and we get loss of power. So we're both right in what we're claiming. And this explains why banding can occur. With an RF tube, I've explained to you how the dot size changes with exposure time. That's not the same as with a glass tube. With a glass tube, the pixels always remain basically the same size. And what you get is a different amount of colour, if you like, in the pixel because the power changes. So what's the solution? So you need to buffer the effect of this refrigerated water that hits your tube instantly and causes distortion to your mirror and loss of power. There is no way that a 1 degree C temperature change on the outside of this water jacket is going to give you a 1% change of power, because what's happening here has got nothing to do with how the power is generated. The power is generated by reflection off of these mirrors. So it's the mirrors that must be distorting that are causing your power loss. Maybe it's these guys that need to look at the problem more and work out how they can reduce the shock load into the tube. Let's start trying to unravel this problem from square one. Right, let's take a look here at this tube manufacturer. I'm not going to mention the name because it may be tomatoes, it may be tomatoes. Now, working conditions, cooling water, and I'll state this very carefully, water with standard water temperature from 10 degrees C to 50 degrees C, and a flow rate of between 2 and 5 litres a minute. More in accordance with what I have found out, that I can push the tube for a large range of temperature and get very little power change. I think we're coming back to the fact that yes, there's not anything wrong with the tube itself. The tube can handle a wide range of temperature difference, but not in the way that a CW5000 throws that temperature range at the tube. So let's have a quick look at what a CW5000 or 5200, how it operates. Remember the flow rate here, let's just say 5 litres a minute. Okay, so here we've got the pump that's used in the CW5000 and 5200. It's capable of delivering 16 litres a minute, which remember is roughly 3 times greater than the flow required through the tube, at a pressure of 36 psi. But there is no pressure number in the tube specification. The problem with all tubes is the limiting factor is the size of the orifice that goes into and out of the tube where the water pipes connect. 16 litres a minute capability out of the pump, but let's just assume that we can only deliver 5 litres a minute with that 36 psi. So let's assume that we are getting 5 litres a minute flow through the tube. Let's have a look at the inside of a CW5000 and see what that looks like. Well, here we've got that 15 litre a minute pump. So it's sending 5 litres a minute out through the flow switch here. And then it's returning that 5 litres here. Now, you all know roughly the size of a CW5000, and I'll ask you the question. How many gallons, how many litres do you think that tank holds? Could I get 5 litres into that tank? In fact, I'll tell you what I'll do. I'm sure that somewhere along the way, it must tell me the capacity of that tank in this system somewhere. Aha! We've found it. 6 litres is the size of that tank. These numbers here, which is the cooling capacity, is about 1.5, 1 3/4 kilowatts, about 1.5 kilowatts. Now that's not 1.5 kilowatts of heating, that's 1.5 kilowatts of negative heating. We've got roughly 1.5 kilowatts of negative heat or cooling inside that 6 litre tank. We've got a pump here which is taking roughly 5 litres a minute out of that tank and returning 5 litres a minute back into that tank. So we've got 5 litres a minute which is being stirred up around that minus 1.5 kilowatts of cooling. That means there is no buffering for that temperature change at all. In less than a minute we're going to get a rapid cooling into these pipes that are running out to the tube. I mean, it's not doing any damage to the tube, but it might be affecting your cutting performance. It certainly affects your dithered engraving performance, as you can see. So I think it falls upon you to deal with this problem with an intermediate buffering tank. This is what I mean about the sort of work that Matthew does. It's amazing work, but it doesn't require super photo quality replication. The crispness of this after IMAGR works extremely well. He's managed to cheat on his CW5000 for just a short period of time, enough to allow him to engrave this without the compressor switching on or off. And as you can see, he's got a band-free engraving. But if you look a little bit more closely, you'll see that he's not free of aliasing on this uniform background. You can see it up here as well. But hey, I'm being super critical. This is still an amazing piece of work. So congratulations, Matthew. So I'm going to finish this session with Matthew's great piece of work and say thank you to Danny and Matthew for their help in actually me understanding what the real cause of this banding problem is on a water-cooled tube. It's taken a long time to get there, but I now fully understand it, and I hope it has been useful for you guys if you've experienced the same banding problems.